Good afternoon, everyone. Thank you for joining us. My name is Marissa Waterman. I'm the Marketing Director here at the Academy. Today's webinar is titled Smoldering Treatment of PFAS in Soils. Our Executive Director, Dr. Daniel Uther, will serve as the moderator and will introduce our speaker today. During the presentation, you'll be able to submit a question by clicking on the Q&A icon on the bottom of your screen. We will do our best to address each question at the end of the presentation. Before we get started, Dr. Uther would like to say a few words. Dan, how are you today?
I am fantastic. Thank you, Marissa. Welcome to everyone who's joining us today. Today, I'm joining you from the road. I'm actually at a conference in Pittsburgh, so just ignore any background noise that you might hear. We've got an exciting, award-winning presentation for you today on a topic that is at the forefront of everyone's mind, PFAS. But before we get into the details of today's webinar, let's pause. Let's take a moment to reflect on who we are as an academy and how we are able to offer today's webinar free to our membership. The Academy is all about leadership and excellence in environmental engineering and science. And our 5-year strategic outcome statement is sharing our stories to grow, connect, and diversify our profession. Webinars are a type of story, rich in great technical detail. And we're fortunate to have patron organizations, utilities, and consultants who believe in our mission and want to support story sharing. And so as we begin today, I'd like to say a special thanks to our patrons. These organizations provide us with much needed financial support, and that allows us to offer these webinars free to our members. Thank you to our patrons. As a reminder, webinars offered by the Academy are vetted by a team of experts who offer feedback on subject content to ensure that every webinar is of value to our members. If you have ideas for webinars, please let us know. We're always on the lookout for great content to share. As I've already mentioned, today's webinar is an award-winning project. Specifically, we're going to hear from the 2024 winner of our Superior Achievement Award. What does that mean? Well, it means this project is the best of the best in our annual Excellence in Environmental Engineering and Science competition. Way back in April of this year, President Wirt and I had the pleasure of introducing this award-winning project for recognition. And today I have the added privilege of moderating this webinar on this amazing work. Our speaker today is David Major, a board-certified environmental scientist and a senior consultant for Savron, a division of Geosyntec, one of our patrons. David has served as project lead for more than 10 SERDP projects, and in 2021, SERDP recognized this work on smoldering treatment of PFAS with an Environmental Restoration Project of the Year. Today, we'll be hearing details of how Savron, a division of Geosyntec, has used smoldering with surrogate fuels, like granular activated carbon, to generate the high temperatures that are needed to decompose PFAS in soils. PFAS, what's often known as a forever compound. David, we're really excited to learn more about this project, but before we begin, let me just remind folks that at the end of today's presentation, I'll be moderating a question and answer session. So throughout the webinar, I invite you, in fact, I encourage you, please put your questions in the Q&A function in Zoom. I'll be reading these throughout David's presentation. I'll be grouping and organizing them, and then I'll use my own judgment and your questions to guide a conversation with Dave about this amazing work at the end. Without further ado, Dave, welcome. The stage is yours.
Well, thank you, Dan. Thank you for that introduction. Welcome, everyone. Today, I'm going to be talking to you about the smoldering treatment of PFAS and particularly field demonstration. And you'll also see through this discussion, my other favorite title for this particular talk is How to Barbecue PFAS. So I'm going to give you an introduction to what smoldering is, because not everybody is familiar what is smoldering and how it's different from other thermal treatments. And then I'll talk to you about the applications, particularly to PFAS. And then I'm going to discuss the lab pilot testing we conducted under the SERDP and the SERDP programs, and also touch on how we're expanding this with other PFAS projects. So what is smoldering combustion? And first off, I'm going to tell you it's not incineration. It's a flameless exothermic combustion reaction that actually happens on the surface of a condensed fuel. It will convert all your organic compounds to carbon dioxide and water, and it relies on the combustion triangle, where you need to bring the fuel, the oxidant, and the heat together in one spot for that process to continue. But what's unique about smoldering is that it needs a porous media to actually occur. And that porous media serves a very special function, as I'll touch on in a little bit later. First off, when we were developing this technology, we relied on the fuel to be the actual contamination in the soil. So for a lot of times, it could be hydrocarbons. We'd have air, which provides the oxygen into the system. And then we have the ignition event using a small heater. It could be a resistive heater that you've used in barbecues to start the barbecue going. And then you take that heat away, and it becomes a self-sustaining process. And as I pointed out before, it's very similar to like a barbecue. And what's interesting about smoldering in this porous matrix, the heat that is released is trapped by the porous media. And that captures the heat and allows it to be recycled within the porous media, raising the rest of it up to the ignition temperatures needed to support smoldering on its surface as soon as oxygen is ejected or comes in contact with it on the surface. Now, with hydrocarbons, what we discovered is that when you have an oily hydrocarbon that isn't typically burned by itself, unless you put it into a vapor phase, and that requires a lot of energy. If you actually mix it in with sand, once you start that initial heating reaction, you call pyrolysis reactions that happen. It basically takes that liquid fuel and turns into a condensed fuel, like a char, which then starts combusting on the surface. The heat that is released is then trapped by the rest of the porous media, the sand, which is very good at retaining that heat, and allows that heat then to be propagated and recycled to heat up the rest of the hydrocarbons. As a result, you get this char formation starting to form in front of the smoldering front as it progresses through the contaminated porous matrix like soils. But with smoldering PFAS, it's a little bit different. We know that we need heat to break it down to hydrogen fluoride and ideally shorter chain compounds, ideally no shorter chain compounds, but that's not completely true. What we do know is that if you mineralization, the conversion to hydrogen fluoride and CO2 and water and that starts occurring at 700 degrees Celsius and actually starts maximizing over 900 degrees Celsius. But we know that PFAS is not a great smolderable fuel in of itself. And that's often because it's present in concentrations in soils that are typically too low to support their own combustion. And if it's really, really high concentration, some things like AFFF will actually smother the reaction itself, and they're actually designed to do so. But how we get around this is that we can add a carbon, and so it can be something like granular activated carbon. It could be anthracite, it could be wood chips, and even the GAC that is being used could be spent GAC. We can use that GAC itself and mix it in to the actual soil that contains the PFAS, and then be able to actually allow that combustion reaction to happen. Well, how much do you have to add? Well, you don't actually have to add a lot of carbon to actually get a lot high temperatures. And this graph is showing you the concentration of granular activated carbon in grams per kilogram and the average smoldering temperature you'll achieve at different air velocities or looking at different air fluxes into the system. And as you can see, basically the temperature can be dialed in by how much carbon you add into your system. In this case, concentrations of at least 35 grams per kilogram of soil of carbon will provide enough carbon mass to generate temperatures in excess of 900 degrees Celsius. And so that's fundamentally the basis of how we're actually going to go around treating PFAS by getting the temperatures we want. And I'm going to also talk about later how we can optimize that to make sure we have fewer shorter chain compounds in the process. I'm also going to talk about two other things that how we apply this technology. We can apply it in situ, which we call STAR, and we can do it ex situ, which we call STAR-X. The project on the left actually won a Superior Award as well, and it was looking at the application of smoldering to treat creosote below the water table at a site in New Jersey. And the project you see on the right involves treating hydrocarbon contaminated materials in Kuwait, and that's involved about 300,000 cubic meters of hydrocarbon sludges mixed in with about 700,000 cubic meters of contaminated sand in Kuwait. And these systems on this right-hand side are called hot pads, or basically engineered structures that contain the key heating elements and also air distribution systems to actually smolder contaminated soils and soil piles. But let's talk about what we do in terms of this particular project. And like I pointed out earlier, SERDP, the Strategic Environmental Research Development Program, provided an award for this work, looking at the actual mass balance of the destruction of PFAS through a lab column test. And I'll be talking about that. And then we also did scaling up of this process and applied the technology to treat PFAS contaminated soils at an Air Force base located in Ontario, Canada. And this is what we also won the award for the superior achievement in 2024. So let's focus on the lab column test. What was really interesting about this test is that we employed a unique column design. Initial work we did on this work was kind of open columns. We're just trying to show that we could remove the PFAS through the smoldering reaction, and we tried to trap and characterize the emissions. But it was really hard to actually, we're getting not a great mass balance because we had an open column at the top. So what we tried to do this time is call it a column within column design. So within the interior column is actually contains the test materials, the sand, the PFAS, and the GAC that we had. On the outside of the column, we just contained the sand and the GAC in the same proportions that we used inside the inner column. And the reason for that was to create a uniform heating front that would travel up along the length, and so we'd minimize temperature distribution or temperature differences between the inside of the column and the outside, and so we could get uniform temperatures through the inner column. And then we directed all 100% of the emissions out to a PFAS emission system. Part of that was associated with just trapping the PFAS on GAC and absorption tubes. And then we also diverted 50% of the flow as well to hydrogen fluoride imprinters to capture the hydrogen fluoride. And this allowed us then to analyze both what was trapped in the liquids as well as what was trapped on the GAC itself on the XAD tubes, and then we could do a characterization of the emissions as well as try to do a mass balance because we know exactly how much PFAS that we would actually add in the system for these experiments. We conducted 8 column tests. There was the first 4 are called baseline. They basically involved adding granular activated carbon at about 50 grams per kilogram. And we also did not have what's called calcium oxide. And the reason why we looked at calcium oxide is we know that it can enhance the decomposition of PFAS at lower temperatures and also can help sequester hydrogen fluoride that is produced. This middle one was a steam injection. We had a theory about looking at hydrogen, improved hydrogen production with steam reformation during this process to allow us to maybe cause better destruction. I'm not going to talk about that because it wasn't that successful. And the last 3 columns were actually calcium oxide, where we added calcium oxide at different concentrations, again, at relatively low concentrations, and mixed in with the GAC and in with the sand, and see how the impact was that. So in the base case, we found significant amount of the fluorine mass, the organic fluorine mass, coming out as hydrogen fluoride. We looked down the breakdown. We had things called the hydrogen fluoride in the emissions. We also looked at PFAS in the emissions trapped on the GAC. We also looked at any of the sand and what happens in the what's left on the sand. And then we also would call burnout tests because sometimes we found that we would lose fluorine mass to the surface of the apparatus. So we did another clean burns, would actually drive off any remaining fluoride in the that may be bound onto the materials in the test apparatus and capture that as well. What we find here is that more 75% of the mass that we found came out as hydrogen fluoride. We found very, very little PFAS in the emissions on the GAC. It was based on the targeted, this is before the 1633 new method, this is method 8327. We saw, again, a fairly extensive analysis, but we couldn't find much PFAS in the emissions. And then we also used another thing called PIGGY, which is also referred to as particle-induced gamma emission. It is a way to measure total fluorine on surfaces of materials, and it will include both organic and inorganic fluorine. But since in these experiments we did not have any source of inorganic fluorine, any fluorine that we get in here is just based on the organic fluorine. Based on the PFAS analysis, we could find that we had very little, we couldn't detect any PFAS, all below the level of quantification, but we still found, based on PIGGY, about 1.1% of fluorine in the post-treatment sand, suggesting that fluorine did react with the silica sand in the system or any and maybe bound to that in some other mineral form. And we also then looked at that total fluorine again in the GAC. We found another almost 22% of fluorine in the GAC, but that can also be caused because we're trapping hydrogen fluoride in the GAC as well. And so we basically think most of it are getting good decomposition to hydrogen fluoride and with very little emissions. But as I mentioned earlier, if you add calcium oxide, you can really improve the PFAS destruction at lower temperatures. And also you get to remove hydrogen fluoride. It's something we really ideally don't want to deal with in the air emissions. So basically the hydrogen fluoride would react with the calcium oxide, forming calcium fluoride, which then becomes an inert mineral phase that should be trapped on the soil. So here's some, this kind of take away, these results here will kind of prove this point out. And this particular thing, we're looking at the pre-treatment concentrations on average and the total fluorine concentration, not individual PFAS, we convert it into the fluorine. Fluorine concentration is milligrams of fluorine per kilogram of porous media. After treatment, we find that 99% reduction in all measured PFAS that was added to the system or any residuals. We did not see anything that was present when we did the treatments. However, when we do piggy spectroscopy, we find that there is still between 95 and 99% reductions of fluorine, but particularly what's interesting is that when we actually look at the calcium fluoride experiments, you see that we're actually, the calcium oxide experiments, you're seeing that we're getting most of the fluorine still retained on the soil. So there is still a little bit of formation of a fluorinated compound or an inorganic fluorinated compound mineral phase on the columns without calcium oxide, but you see most of that fluoride is now retained on the soil in the presence of calcium oxide. And we verified that by doing XRD analysis, which showed that we're getting the formation of calcium fluoride compared to our blank calcium oxide pre-treatment compared to the calcium post-treatment. So the fluorine mass balance, when you look at without calcium oxide addition, with calcium oxide addition, you're finding that mostly all the soil contains the calcium fluoride, and all the targeted PFAS are below the level of quantification. There was very little hydrogen fluoride being released in the emissions, well, greater than 90% reduction compared to the base cases. So the key column results can be summarized as follows. We can achieve over 900 degrees Celsius with these 40 to 60 grams per kilogram of carbon per kilogram of soil. We have 99.9% greater reduction and below detection limits for the PFAS analytes. We see that you get a reduction of F-mass without calcium oxide, but you have no change in the total fluoride mass in the soil with calcium oxide because it's being sequestered as calcium fluoride. And the emissions, we had less than 0.02 to 0.13% of the initial F mass in the columns came out, with lower amounts coming out when calcium oxide is present. And this is consistent with having less hydrogen fluoride and shorter chain compounds being produced. And also with the total mass balance in the system, we range without calcium oxide between 68 and 109%, and with calcium oxide, a bit better mass balance, 80 to 128%. That's the range in each of those, and reflects actually the analytical errors in the system. In both cases, we're pretty well close to 100% of the mass balance when you actually look at it on average. So we then moved this idea out to the pilot scale test. And this was really to look at what happens with real soils, and we wanted to verify this. And so we did these experiments using our mobile hot pad systems, our pilot scale hot pads. And these are just, as you can see in the top corner there, we have an integer structure. It's got a screen on the floor, underneath which is the plenum that holds heaters, resistive heaters, and also our air distribution system. We have a retractable roof, and we can then connect this up to our air emission and monitoring system. So how we'd anticipate actually working with this is that obviously you would have a soil stockpile. We mix that with the GAC. We then put it into our hot pad. We do a treatment. We collect the gases and have air treatment. Then we do bring out the clean stockpile and repeat that process in a batch manner. At the Canadian Forest Spaceport, which is between Toronto and just north of Kingston, Ontario, this is the setup of our pilot test system. You can see the hot pad set up on the right-hand side. We have a knockout cylinders. We then move through to treatment through. We measure the continually the CO2 and carbon dioxide and oxygen levels to verify the smoldering process. We also have the ability to then take samples directly from those lines, and we then pass the emissions through a gas treatment system to verify the to basically off-gas treatment for anything that may be released from the pilot test. And here's some pictures. I'm going to show you just how we set this up. Here's using yellow metal.
Dave, apologies for interrupting you, but it went off your slide share. So if you can go back and reshare those slides. We're back to seeing your lovely face and not your slides right now.
Oh, goodness.
Well, I actually see the slides.
Okay.
Okay. I can see, I just got the share. It still say I'm sharing right at the moment.
All right. Thank you.
So at this point, you're seeing the just us mixing using yellow metal to mix the soil that's been excavated. We're adding calcium oxide with the white powder you see there, along with the activated carbon, and we're just mixing those together manually until we visually it looks like it's been mixed. We then load it into the hot pad using the backhoes, and then we can see we fill it up to the top. Now, towards the top, what we did put down here is an extraction line on top of that soil for gas sampling before it got put off to the emission control system. We could draw raw vapors off the top of the pile as the smoldering went on. And we covered that pile also with a limestone cap. And that was for us at the time, being absolutely sure we're not going to release any hydrogen fluoride. And at the same time, we also installed thermocouples to measure the progress of the smoldering front as it moved through the soil pile. And here you see the whole system set up, and we're saying we run it, 24/7 for about 5 days for the treatment. And then here you see it being excavated. The soils come out very dry, and a bit of a reddish tinge due to the oxidation of the iron in the soil. And we also, the point of this particular graph is to show you generally the kind of thermocouple temperatures we got within the different parts of the hot pad. We can see temperatures exceeding like 900 to 1,000 degrees Celsius in some locations. The overall temperature average on most of these are typically around 900 degrees Celsius. But what's really important here too is to note that how we did our emission sampling, because we're going to be touching on that. So the yellowish bars indicate the time frame where we're collecting materials and directly sampling for PFAS through our emissions sampling system. The purple represents where we direct all the emissions to a hydrogen fluoride trapping system. And the red line represents where we took a raw summa samplers before and after the actual gas air treatment system. So it'll give you an idea, just like, we did a fairly extensive emission sampling, which was important with us with respect to understanding how good our mass balance in the system is. So the results, cut right down to the chase here, is that we looked at both the targeted and non-targeted analysis using the LCMS. We did TOPA analysis for total precursor analysis. We also total organic chlorine. And the numbers in brackets is converting the sum of the individual PFASs that were present in the system to their organic fluorine equivalent. So we can look at that. And as expected, when you look at the TOPA versus the LCMS, you see higher concentrations because there'll be non-targeted compounds are being converted into something to be analyzed as part of the TOPA process. And then obviously we're getting other precursor compounds that are not picked up in the general LCMS method. But the bottom line is, but we did 2 pilot tests, each 10 cubic meters. We see over 99.9% reduction in concentrations. And we're also seeing basically we had very little coming out in terms of the fluorine. There was some compounds picked up in extracted in the XAD tubes used for trapping PFAS. They were typically 2 to 3 chain length carbon fluorinated compounds, like TFA, for example, is probably the lower 3 chain compound we picked up. But all these compounds that we would be potentially remitted would be actually captured by vapor phase GAC, and so we can actually keep it completely treated, and we can actually use that GAC for future treatment piles as well, because we can mix the spent GAC into the soils for future treatment, so we can basically deal with any kind of PFAS emissions that come out here through subsequent treatment in other batches. We did the solenoid canister, and this work was done with Kurt Pinnell's group down at the Brown University. And what was very interesting is that we actually found fairly long chain compounds that may have actually had fluorines on them. This has been shown that sometimes during thermal treatment you can get the formation of longer chain compounds when they reconstitute, when they cool down. But what's interesting in this is that in our lab air, we found some of these compounds as well. So they're around us. There's only 2 compounds that were only detected in one of the pilot tests, and they're very, very strange compounds, and they had very poor matches. And so we also did not see anything like this in any of the GAC sorbent tubes as well. So what we can take away from this is that we don't think we're actually producing anything that's unique in terms of new fluorinated compounds, and anything that is being produced is very long chain, and it definitely could be treated by vapor phase GAC. So the key pilot test results on this is that we have over 99.9% removal. We get confirmed sequestration of soil calcium fluoride, so we're very low concentration of total fluorine being emitted as PFAS or PFAS derivatives, and less than 1% of total organic fluorine was emitted as hydrogen fluoride, which is all very consistent with what we see in the lab tests, since we're demonstrating that we can take this and scale it up and make it a very viable technology for treating contaminated PFAS soils. So what other projects we're working on? I thought we've expanded beyond this particular project, and we've been actually also funded by the ESDCP, which is the Environmental Security Technology Certification Program under the Department of Defense. And what they were looking for is more rapid on-site treatment. Then, as I pointed out, we have this pilot scale system, and then we have these large systems, which are much more engineered plants and great construction. We need something that allows rapid on-site treatment, can be deployed in remote areas, low power requirements. So we needed something more scalable. So we developed this new thing called Star Express, and it's a very mobile 35 cubic meter system that we can chain link together to treat increasing volumes over depending what throughput we want and on time frames. And we're actually doing this demonstration at the Joint Base Elmerdorf-Richardson, or JBER, in Alaska. There are 2 other technologies being compared on this. There is another 2 thermal desorption processes being looked at, where they desorb the materials from the soils and then treat the off gases. Ours is an on-site destruction technology, hopefully 1 pass. And our goal is to be able to treat 500 cubic yards of PFAS impacted soil. So we've developed this, we fabricated this system. These are to make it really simple to operate in the field. We did manual tilting roof sections. It can, with 1 person, can actually open and close these vessels, or what we call the F-35s. The entire design, the structure is just not a container box that we modified. It's actually developed to actually have the structure include the air distribution and condensate collection lines and extraction lines with doors that swing open at their end, make it very simple. ISO lifting points, we've designed these so they can actually be manually using very simple systems to actually manually take it off a flatbed and put it onto the site, or use the forklift. And then we have a containerized balance of plant, which includes all our blowers and extraction systems, as well as our controls and continuous emission monitoring the systems and condensate knockout systems. And here it's in some pictures of it. You can see it being fabricated on the left, on the right, top right. You can see just a manual lifting system that we can use. If you have to work in remote locations, the bottom left, as you can see, the actual controls room with our breakers, as well as our air emission monitoring system. And on the right, you can see the balance of plant site where you got the blowers and air ducts and sampling locations as well. So the nice thing about this is how we could set it up. Here's the site that we're setting up at Jaber, and here's the site before we arrive. We come out the flatbeds, we hook everything up, and the whole design is for plug and play, so we can hook up the piping and the wiring very quickly, and then we have the system set up within about 48 hours and ready to treat on the site with a footprint of about 100 feet by 100 feet for operational area. So very deployable, and we're now started to do our first few commissioning batches right now to do a shakedown, and then you can see the soil being loaded with a very thin, clean cap on the top, just acting as a heat sink. And then we have the treated soil after, which we're now setting off for analysis. So this project is ongoing, and we're anticipating that we should be finishing up within about another month, and then we'll be deploying from the site. Another way we're looking at applying this technology is also in situ. And I talked about the STAR process. And what we're trying to do here, develop an injectable fuel that will support smoldering combustion and will provide sufficient energy to either volatilize the PFAS or cause them to be destroyed, along with any co-contaminants in source areas. This particular project is going to be conducted at Joint Base Cape Cod in the Fire Training Area 1. It's all about treating about 500 meters of source area and soil volume. One of the things that we've been looking at is how to develop a particular carbon mixtures. We've been looking at the various costs of commercially available colloidal activated carbons, powdered activated carbons, and multiplied vegetable oils. Can we mix those things together? Initial work, we found that we could actually get really good temperatures using mixtures, and which gave us some ideas on how we could potentially make it injectable. But one of the things that we found out is that there's very big differences in the cost of all these materials, and you need to have to pick the right compound. And I'll get down to that in a second here. And then there's you need sufficient carbon and calcium content. We need to provide sufficient carbon into the subsurface to make this work, and it has to be easy to handle. They have to be stable. We have to be able to do maybe potential add surfactants, which can be very expensive. And the viscosity has to be pumpable, less than 2,200 centistrokes. So during this development, we tried initially looking at colloidal carbon and EBO, because it's to make a slurry. But the problem is when you add calcium hydroxide, you have some problems trying to get the amount of calcium in the system. As a result, you can actually form soap, which is not very pumpable. We did found a product called Flexor, which is a very powdered form of activated carbons, almost colloidal. And we can just add a calcium hydroxide and water mixture. And you can see on the right is the mixture of that. And you can see this graph is basically showing that with this is placed inside a soil column, mixed with soils and treated, we can find that we're getting a fairly decent high temperatures, well, 900 degrees Celsius. And so it's definitely a very viable mixture to work with. We went further on to treat to verify that we can actually work at a reasonable scale. And so we developed, we have what's called intermediate scale reactors, which allows us to mix larger volumes, and we can do pre and post treatment soil evaluation. In this particular test, we took site soil from the fire training area. We had average concentration, PFOS and PFOA, which dominated the contaminants there, around 68 micrograms per kilogram. And after treatment, it was less than 0.1 microgram per kilogram, and we're pretty well, even then, we're running very close. If they're present at this after treatment, they're very close to the detection limit. And we're still waiting for the emission samples to come back. We did a very exhaustive and extended emission sampling program that almost was equivalent to the OTM 45. And right now, this project is looking at a field demonstration in August. And how we would actually implement this technology is through a soil mixing with the dual head augers that will pump it into the source area. Into this, we can then put our what we call injection wells, which actually are 2-inch carbon steels with about a 1 foot long stainless steel well at the bottom. Into this, we can put our 9 kilowatt heaters and then provide air and heat at the same time. And as soon as we detect the combustion gases forming, we can then turn off the heaters and then continue with the air injection. You get this hot front of smoldering that will migrate through, and it happens underneath the water table as well, and progresses outwards into the rest of the contaminated media. And so we'll be putting about 4 of these points in with a lot of thermocouples to track the combustion front within the source area we're going to be treating. So in summary, PFAS are going to be sexually destroyed using smoldering. We need to use a surrogate fuel to get the temperatures we need. We can get PFAS concentration below the current RFLs for the EPA's promulgated. We have a less than 1% of fluorine can be emitted as PFAS breakdown products, which can be trapped onto air, vapor phase GAC. And we also have calcium oxide addition, or natural calcium that can be present in the soil, can allow destruction at lower temperatures. And we can also then co-treat these materials as well. We've got contaminated GAC. We can actually mix with contaminated soils and destroy and treat both solids as well. And we have additional ex situ and in situ field demonstration in progress. One thing that might be also germane to all our listeners here who are in the water industry, we actually have some lab studies going on which show very successful treatment of biosolids using this, where we can actually mix in some things like wood chips and things like that into biosolids without dewatering them too much, and actually also destroy the PFAS as well. At this point, I have wrapped up my presentation. Oh, sorry, the most important part, acknowledgements. I want to talk about the people who've actually helped make this happen. These are my colleagues at Sabron. There's Brian, Laura, Jorge, Josh, and Ben, that do a lot of the heavy lifting and making sure the field programs go well. But also want to talk about Kayla Weber and David Patch for their RMC, Royal Military College of Canada, who've been instrumental, particularly at the beginning of this project when a lot of the new methods were not being developed. They were developing a lot of these methods for analysis of PFAS. At Notre Dame, we had his team, Kyle Dudrick, and his grad students have been very helpful developing and helping us with the PIGI analysis that actually was initially developed by Graham Peasley. Of course, target and non-target analysis by Kurt Pinnell and Kate Mance. And our inspiration is Jason Gerhardt, unfortunately passed away from a battle of with glioblastoma a few years ago, who has been a big inspiration for us, who's really helped us. He was one of the original discoverers of using the smoldering process to destroy contaminants in situ. And it's always in our thoughts, and he's always been drove us to try to do our best and always discover new things. With that, I will then turn it over to the last set of questions, and I'll turn it back over to Dan.
Thanks, Dave. So Zoom got me in the middle. Fantastic presentation. Fantastic. Somewhere in there, they've added this new function where you can not see the presenter slides if you want. I don't know why anybody would want that, but anyway, it's there. So we got some great questions in the chat panel. I've also kind of put some together. Let me kind of break it down about how we're going to take this through, and then we'll kind of come back and pick them off kind of one-on-one. So up front, we had some people asking kind of like, you know, the questions about the soil properties, right? Like, so we're thinking about doing this in soil. So we got to think about the properties of the soil that goes with this. So like, you know, what temps and what properties of soil, and, you know, what's the radius that this works at, and what about the pore water, and, you know, does this sterilize the soil? All of that kind of stuff, including the fact that it feels like it's got some requirements for air to pass through it. So it's got to be some interesting porosity. So some of these, let's talk a little bit about understanding the soil properties and what limitations that might put on where we can use this. The second was that we got questions in this space that really drill down in the weeds of the process itself. Waste gas that's coming off. Could this just end up with something volatilized in that pops off? I mean, you looked into that, but you know, folks are ultimately looking, is this a destruction? And do we know it destroys everything? You did your mass balances, but we'll talk a little bit more about that. But then can we take this in situ? Can we, you know, you showed, you know, the concept of actually going in the ground. People are in this space about, okay, well, what about a permeable reactive barrier? I've got carbon that I might be using in other things for other places. PFAS is this forever compound. We seem to be finding it everywhere. So we might have co-contaminants. You already spoke to this a little bit about the biosolid, just a potential other fuel supply. What about spent carbon coming out of drinking water that might have some PFAS on it because there's some absorption properties there? So, and then a weedy detail question. What exactly is going on with this calcium oxide? Like, help us understand, like, a little bit of the chemistry of what's going on with that in the surface and exactly how that's so critical a part of this system. Folks then wanted to know about some access to published results. Where can they find a little bit more about this? And then, of course, we always want to know the questions about, the education for the future folks. So, PFAS has kind of caught us all, not unawares, but caught us all, like, as you and I were talking in the green room ahead, pivoting from one problem to the next problem. This is the problem du jour. And so, how do people keep themselves educated to participate in this problem, but then be on the front foot for future problems? So that's kind of the space we'll talk to, if that's okay. And we'll look and see if we get some others that bubble in here, but speak to us a little bit about soil properties, right? So is this, do we mean soil or do you mean dirt? Because when I think soil, I think, the first couple of feet of soil horizon, and there's worms and grass. And what do you mean by soil?
Anything that's a permeable material that water can flow through, more or less. There's a good question. This process requires air, and air has to be able to move through and support the smoldering process. And there has to be sufficient air flux or oxygen flux to achieve the kind of temperatures that are necessary to progress this process through the soil and affect the heat up through the soil column as well. So in terms of how we've applied this technology, even with hydrocarbons, we kind of say, like, silty sands or silts will probably be definitely smolderable. If you're in situ, it becomes a little bit more challenging because you don't have as much control on things. But ex situ, we could definitely, with the combination of mixing, or we can even bulk up the materials, the other porous media, to help improve the airflow through that. The biggest impact also is that the airflow drops down low. It actually just affects the processing rate. So it takes longer to move the air through. The smoldering front doesn't progress as fast, and as a result, it's going to take longer to treat each batch that we do. But we can tolerate a certain percentage of clays and stuff like that. But the key aspect, we need to maintain at least a certain amount of minimum air velocity through to actually to maintain the smoldering front. People often ask, well, what happens? What's the soil like after that? Well, it is sterilized. All the organics are completely gone. There's not going to be any organic materials left. There's a variety of studies out there that show that these materials will become repopulated. They're on the surface, but different mosses will grow on them, and deposition, fungi. Work has shown that in the subsurface, background, the sterile field is an optimal ground for new bacteria to come in and start populating and reestablishing the ecology there. It does take time, but it does definitely regenerate. And we've also done some studies where we've actually did plant studies. And, for example, over in Kuwait, we've actually got plots where we actually took the soil that was not treated, soil that was treated, and it's grown native grasses on them with minimal amendments, and you can add simple amendments on carbon, nitrogen, phosphorus into those soils to make them more readily a support for plant life. So it's all very, very manageable, and you can reuse the soils, and also from a geotechnical perspective as well.
Makes sense. If we've ever been to Hawaii, we know that we can eventually turn pretty sterilized stuff into pretty green stuff. So
That's true. That's true. So there's some other, you said there's some more into the weeds, so to speak.
Well, and so, the airflow requirements, so you spoke to that. I'm imagining, obviously, there's no water left in this, after that kind of process, no organics. You were mentioning 900 degrees C. Is that are we talking some range there? Is that the target temperature for the PFAS? Do all PFAS, PFOS respond to the same temperature? Is it, how does that play out?
Typically over 900 degrees C, you're going to see everything start decomposing. Put perspective, incinerators, I'd have to think. I'm going to quote a number, it probably might be wrong, but to destroy PCBs, you have to hold it at and this, I'm got to remember flipping between Celsius and Fahrenheit.
Right.
I think for Fahrenheit, it's 1250 for so many half a second or a second or something like that before you destroy those compounds. Remember, when we're doing smoldering moves it's very relatively slow. We're moving like centimeters per hour through the soil column at fairly high temperatures. So our residence time within that smoldering area is relatively high. Now, there can be, we know that some of these PFAS will volatilize at temperatures of 350, 400 degrees Celsius. But the smoldering front is really, really tight and really, really narrow. And I mean, to give you an example, when we do these experiments in the columns, we can have our thermocouple separated by 3 centimeters. And once the thermocouple that's experiencing smoldering could be like 1100 degrees Celsius, and 3 centimeters away, it's 70 degrees Celsius.
Oh, wow.
Because the soil is such a great insulator and really holds that heat in. So even if things are volatilized, they'll probably condense back out and reabsorb onto material. So we'll probably be able to eventually get caught up with the next batch. So there'll be a certain amount of material that might volatilize and get out towards the top. The heat front progresses far enough away that it's no longer not likely these compounds are going to escape rather than actually being trapped. But I mean, we can do things like in the cap, we can add a little more activated carbon to actually a place absorbed and then gets burned. And so that's why we don't get a lot of volatilization and loss in the system. Why we don't get most of it gets destroyed. And the piggy analysis kind of really showed that. We in the column experiments, most of the mass was found as calcium fluoride. It was not found in the emissions, and the hydrogen fluoride levels came down substantially. So we were pretty confident with respect to the destruction efficiency of the technology. And to point out what, go ahead.
I was going to say, and that kind of points to this question, right? Like, so you get those kind of temperatures. What do you volatilize? Where else does it go, right? Because it's not incineration, it's smoldering. So can it escape? And I think that's what you were looking at with the hydrogen fluoride and the calcium. And so that was one of the questions that had come up, is kind of like, help us understand the chemistry. What exactly, because it feels like you got to have the contaminant, you got to have the fuel, and you got to have this calcium oxide in there so that it grabs it and keeps it there in terms of the calcium fluoride. So
there's a good paper that's just actually helped review as well, but Kyle Dudrick's group put out, where they did some experiments looking at various earth metals and their impact on the destruction of PFAS. And what happens, the calcium seems to act as a pseudo-catalyst. It seems to actually help that basically cleaving off the ends of the PFAS during the temperature process. And I'm aware of another paper, I believe, where people are looking at the role of actually when the PFAS are bound to carbon, actually the carbon helps when it's stretch the molecules to a certain extent to allow them to be decomposed as that material gets heated. So there is not that I don't want to. I'm not perfect. I'm not a great analytical chemist or an organic chemist here, but at the same time, from a simple point of view, it appears that these compounds, and based on the papers that are out there, they do seem to enhance, when they're present, the PFAS enhance the destruction as the temperature goes up, because they act as pseudo-catalysts or help somehow make the molecule more available for oxidation reactions.
Okay. Now, if I was an incinerator, I'd be imagining I need an air permit, et cetera, right? If I'm a smolderer, do I need to go that far? Because, that's where I was trying to think. So what's the chance of this stuff getting out there? And do I have to measure those off gases?
Well, we're doing a lot of at the DIU project, which is the Alaska project. We are doing an exhaustive analysis of using the OTM 4045, which is the new EPA method to look at stationary emissions from PFAS, and it's a very complex process and very expensive. So we're be collecting that data. Our systems were kind of like pre-OTM 4045, very similar in some ways. We'd be able to actually see where things are going. We're trapping as much as we have. We actually, another project we did as well at Edwards Air Force Base, I did not talk about, was that which is just finished up, we're still getting the data for it, is also we used resin to help actually trap PFAS. We're trying to look different methods to try to quantify with that. Everything we're seeing suggests that the amount that's being released is very small, and if it is released, there are compounds that can be treated by vapor phase GAC. And if that's the case, that GAC can then be used for the next, eventually when it gets exhausted, we could use it in a fuel source to treat other soil piles.
That's where I think people were going that way in the questions, right? So, okay, so I've got a drinking water treatment. I use some kind of carbon approach. Now, what do I do with my spent carbon? Okay, well, I turn it into a feedstock for some soil treatment, or let's say I got a groundwater plume and I put a permeable reactive barrier and then I burn it up afterwards, like a grab and burn kind of, can you speak to those in terms of the over the horizon or what's next? Or
yes, well, a couple of things. First off, we are currently doing experiments in-house where we're looking at the treatment of pure phase GAC. First off, we want to be sure the temperatures we get don't melt the reactors, because they're basically almost like a blast furnace if you do it right. But what we're finding is that we can control that because of the air flux, because it becomes once it becomes oxygen starved, the temperature just stops rising. And so we did some initial experiments. We can get very hot temperatures, but definitely very manageable, just treating pure GAC that contains PFAS. So that's what we've done the experiments to verify that we can actually not melt the reactors, but now we're going to be doing experiments with actually treating PFAS contaminated GAC and measuring those byproducts in that as well. So that's one area. And the other, let's see, there was that. The barriers. I know we've pitched, and part of this ESCG project is kind of a proof of concept as well. If you have enough carbon in these groundwater treatment barriers, which are using colloidal or powdered activated carbon to create these barriers to absorb the materials and allow clean water to go through, at some point these walls will become exhausted. And if there is sufficient carbon in there, we could definitely smolder them out. But you do need to add sufficient carbon. Now, usually the application of these colloidal particles are they're probably at the most like 0.5 gram or 1 gram per kilogram, and we kind of need a little bit higher than that to make it work. So either people have to, after they do a bunch of regenerations of that, then we come in and treat it. But it's something definitely a very viable approach.
Okay. So there's some options there for some crossovers. Yeah, of course. Okay, so that it kind of makes sense because we're all looking for something to deal with this, right? And so, carbon's a go-to for a lot of things, and then what can you do with the carbon after? So it's fascinating to think about. So from an operations standpoint, right? So this does not feel like much of I'm a charcoal griller, so I know what it's like to be out there on my charcoal grill, and I don't get too far away from it to make sure that it's behaving the way it's supposed to, or I will end up now. I realize the temperatures we're talking about here and all, but it takes a certain level of kind of an art of operation along with some good monitoring and some good feedback. And I imagine once you get to 900C, you can burn that steak pretty quickly. So how does that go in terms of an operating strategy if you're setting this up? I mean, is this going to be 24/7 and people have got to be on it all the time to be able to make it work?
No. Our experience is showing, particularly with like PFAS contaminated soils and doing this procedure, it's actually in some ways actually simpler than actually doing hydrocarbons. Because hydrocarbons, you have to deal with a lot of oil mist, you can get flaring, you can get a lot of other issues. This actually burns pretty clean. And the way we monitor things, the things that we look for condensate management. We know and make sure we're going to have wet soils. We're going to produce condensate. We do have a way to collect that and measure it and verify that, before we discharge. We also have a lot of thermal monitors. We monitor, we have thermal profiles in the soil. That allows us to make sure we know where approximately things are going. But we also really closely monitor the airspace, the temperature coming off the top, which tells us that it's safe to operate and stuff like that. And on top of that, we also have a continuous emission monitoring system. So looking at what we call the combustion gases, oxygen levels, CO2 production, we know when the smoldering is started, and we know when the smoldering is ended. And so we can then know that it's time, it's safe to open it up. And we have very protocols for like what we call hot unloading. Now, the soil is cool, but it's still not something you want to touch. And so we basically know how to unload that quickly under relatively hot conditions. But the soils do cool, because by the hot soils are more towards the top, but you got a lot cooler soils at the bottom.
And then how's this going to play out with convincing regulators? Because again, I'm thinking about, like by the analogy, right? Like, I've got kind of a multi-barrier water treatment system, and I can switch to this amazing membrane, but all it takes is a couple of pinholes, and now suddenly there's some stuff coming through, right? Now, just conceptually, right? Now, I go over here to this smoldering. It's going to work great as long as everything heats up enough and as long as everything gets going. But all it takes is maybe a space that doesn't quite work right, and then if I left some stuff behind. So it feels like that this is one of those, like, almost to deal with PFAS, it's like almost an all or none thing. Like if this is going to be the go-to to get rid of it, then we got to be confident it's going to get rid of it all at one pass. And so can you speak to that a little bit? Because I imagine the regulators must be thinking about that.
Of course. I mean, it's going to be at the beginning of this. We're doing extensive sampling of our batches, probably way more than you do for any soil treatment. For some sites, you take one sample out of 200 cubic yards of material, and that's considered representative.
Right.
We take about 20 samples within 135 cube area, and then we composite into 2 composite samples. And we're analyzing for everything that you can think of in those soil samples. In terms of including metals, we're looking at any other COCs that are present or being analyzed for, and also in our traps. We got the OTM 4045 methods that we're currently doing to understand that. Now, that being said, one of the things that we can do to help make sure we get uniformity in that is really focusing on making sure our materials are well mixed before we place them in. So we try to minimize, like you got all your carbons at one end of the system and not at the other, and then you're going to have not untreated one end and more treated the other. But the other thing too is basically because of the batch process, we can test stuff, and then if we say, oh, it's not baked for it, we can run it again if we have to. It's not a one and done. If necessary, we have the opportunity to mix partially treated batches together and mix it with another batch and maybe with some of the spent carbon. So we've got some flexibility to actually handle those kind of issues as they come up. And people have been people have asked about permits. That's a good question because I don't think I think a few states are looking at some air levels, what they're allowed, or permissible loading levels in the environment. And I think as we're collecting all our data, we'll be able to answer those questions and give regulators confidence that we understand the process. We know how to treat the materials through a vapor phase GAC, and we know what it takes to load up that GAC, so we know the lead lag and what the breakthrough profile should be like, so we know when to swap things out. So I think those are good operational questions. I think they're all manageable. And we've got a whole bunch of projects. We're collecting all that data, so it'll help us have those discussions with regulators about permits if required.
Got it. Well, one of the questions we have is future, right? So folks that are coming on board, folks that are thinking about this, folks that are switching careers.
I think we lost them.
Okay. Yeah. So if you could talk about, what future environmental engineers and scientists, how maybe they want to go about studying and where they want to go from there, that would be great.
Okay.
Perfect.
Well,
Thanks, Marissa. Thanks for jumping in. Yeah, Dave, that'd be great.
So first things is that there is more and more information out there, webinars. The ESCCP and SERDP have a great webinar series. All the projects I've talked about here are on the SERDP and ESCP web pages, and you can download information, reports as they become available. So there's a lot of information. The ESCCP and SERDP are funding like all sorts of everything from toxicological studies all the way through monitoring and analytical and treatment technologies for water and solids. So it's a wealth of information through that particular organization. There are the papers. We're trying to publish as much as we can. You can go to our webpage, it's www.savronsolutions.com. We do a list of publications on there that and so that's a great little quick resource in the area of smoldering and PFAS or smoldering in general. So there's a lot of good references there, and some of those references are downloadable because we're allowed. There's open publications, and some of the ones will at least give you a link to it so you can see the abstract and you can decide if you want how you can access it from there. In terms of I just know that every university has probably got a PFAS program and looking at this at some level or another. I'm aware of certain research programs like Notre Dame, for example, which is doing a lot of work in this area as well, and Colorado School of Mines. They have great research programs going on there. So it's, I guess, it's looking out through the who's doing PFAS. Just type of PFAS and professor, and you'll probably get a whole host of people and papers that you can get access to understand what's going on. So yes, I think there's a lot of references out there, a lot of resources. The other good place to actually get a good background, if you're not familiar, is the ITRC.org site, the Interstate Technology Regulatory Cooperation Group, Council. They have great manuals and discussion documents and spreadsheets about the latest in PFAS, how to understand them, what technologies are out there. So they do technology reviews as well, as well as also a great way to keep up to date with the latest in regulations, not just in the US, but also international. So it's a great resource as well for people to look at.
And then for students, in terms of, I mean, is this, are there things they should be aware of? Should they, go all in just for PFAS, or should they go all in for being an environmental engineer scientist and realize that PFAS is today's treatment du jour?
So I can only talk about my experience. When I started in this business many, many years ago, I was part of the University of Waterloo. We call it the University of Waterloo Mafia because we're very much into the state and transport of chlorinated and denappled dense non-aqueous phase liquids. John Cherry and Bob Gillum as well. And when I graduated, there was very little known about these compounds. It was just the very beginning of the whole chlorinated solvent field and understanding. Regulations have been set yet. We didn't know how to sample for these compounds. We didn't know the interferences. We did not know how they move through the groundwater or move through the surface, move through the air. We did not understand how to actually treat these compounds. Is it good to be treated? Were they kind of like forever? Like, we're looking at 1,000-year-old sites to clean up. And when I got into that, it was like, literally, you have any expertise, people are banging on your door because they're desperate for that. And I see the same patterns I see with PFAS and that I saw when I started in this environment, as I'm seeing that today. And I'm seeing a lot of people are asking the same questions. How do they move through the environment? How do they behave? How do they interact with other compounds? Do they biodegrade? Can you develop new enzymes to destroy them? Can you, what technologies, can you use? Can you use radiation? Can you use UV light? Can you use smoldering? Can you use that? How do you sample them, and what's representative sample in the site? These are all big areas. I mean, I know a big driver is going to be just the cost of analysis for these compounds. They're very expensive. Rapid screening tools, rapid ways of looking for these compounds in the environment so you can make in the field decisions quickly in a big area. Developing new techniques. There's a lot of really interesting. You just have to type in PFAS and biodegradation in Google Scholar, and you're going to get a ton of great people who are working on all of this, and find out what you can, who you should be talking to and who you want to go and be a grad student with. So this is a booming field in my mind right now. It's a particularly a worldwide phenomena, much more developed probably in Australia and the United States and Europe, but there are more and more regulations coming in. It's a big issue, and people have no idea how to really deal with this on a global scale.
Excellent. David, thanks again for a fantastic presentation. Again, congratulations on winning the Superior Achievement Award, and thanks to Savron and Geosyntec for being a patron of the Academy. We're really appreciative of having you here. We'll turn it over to you, Marissa, to wrap us up.
Okay, thanks, Dan. Thanks, everyone, for all your questions, and thank you to David for sharing your knowledge with us today. We do have several webinars planned in the near future, so you can go to aaes.org/events and you can reserve your spot. Just a reminder, if you're not yet an AAES member and you're considering joining the Academy, please email me to discuss our membership options. My email is mwaterman@aaees.org. And our PDH certificates for this event will be sent out shortly. That's all for now. We enjoyed being with you all today. Thank you so much and have a great day.
Take care, everyone.
Bye.
Bye-bye.